This is Euclid Book 10, proposition number 13. This is the diagram. Okay. It says, if two magnitudes be commensurable and one of them be incommensurable with any magnitude, the remaining one will also be incommensurable with the same. Let A and B be two commensurable magnitudes, and let one of them, A, be incommensurable with any other magnitude, C. Okay. So the first thing we're going to say is that A is commensurable with B. But we're also going to say that A is incommensurable with C. Alright. I say that the remaining one, B, will also be incommensurable with C. For if B was commensurable with C, okay, let's say hypothetically that B was okay, we're going to say that B is incommensurable with C, but hypothetically we're going to say that now B is commensurable with C, okay, and we already said that A is commensurable with B, which means if we go through the whole thing, that A will be commensurable with C, and we just said that A was not commensurable with C. That leads to a problem. Alright. So let's go through the rest of the proof. For if B is commensurable with C, while A is also commensurable with B, A is also commensurable with C, and this is by Euclid Book 10, proposition number 12, which we just covered in the last video. Okay? But it is also incommensurable with it, which is impossible. Therefore, B is not commensurable with C, therefore it is incommensurable with it. But this thing has a lemma. Given two unequal straight lines, okay, we have two lines, this is one line, this is the other. Given two unequal straight lines. This one is obviously going to be longer than this one. Okay. Now we have to label the lines. Okay. See the labels? Now this has nothing to do with this up here. Forget all this. This is what we're going to concentrate on now. Given two unequal straight lines, define by what square the square on the greater is to the greater than the square on the less. If you're confused, don't worry. We'll get you unconfused in 2 seconds. Let A, B, and C be the given two unequal straight lines, and let AB be the greater of them, which we've already established. Thus, it is required to find by what square the square on AB is greater than the square on C. Alright. So now we're going to describe a semicircle. What it means by that is we're going to draw a semicircle, which we did. Let the semicircle ADB be described on AB, which we did. And let AD be fitted into it to equal C. Okay. So now, we're going to say hypothetically that the length of AD is identical to the length of C. I know it doesn't look that way right now, but that's what we're going to say hypothetically. We could actually erase a little bit. We have a nice little eraser here. We can erase that just a little bit. That look a little better to you? Okay. And this is by Euclid Book 4, proposition number 4. Book 4, proposition number 1. Let DB be joined. Okay. Now we've drawn a line from D to B. That's what we've done. Okay. It is then manifest that the angle ADB is right, and this is by Euclid Book 3, proposition number 31. Okay, now we're going to say, I'm going to draw this right here for you so you can see it for yourself. Now we can say that angle ADB is right. That's a 90-degree angle right there. Let's go on. And that the square on AB is greater than the square on AD. And that is C by the square on DB. This is by Euclid Book 1, proposition number 47. Okay. So, if we were to have AB squared, it would be greater than the square of AD. So if we had AB squared, basically what we're going to say is that does that make it a little easier for you? AB squared is greater than AD squared. But how much greater is AB squared than AD squared? Well, if we go to Euclid Book 1, proposition number 47, we say that the square of this side and the square of this side equals the square of this side. So, DB squared plus AD squared will be AB squared. So how much greater is AB squared than AD squared? Well, it's going to be by DB squared. Okay? And that's what they're trying to say. Similarly, also, if two straight lines be given, the straight line on the square on which it is equal to the sum of the squares on them is found in that manner. Okay, what does that say? Well, it says, let AD and DB be the given two straight lines. Okay? So now, we don't know all this yet. Okay? We don't know all this. All we know is that we have a line AD and a line DB. That's what we know. And let it be required to find the straight line, the square on which is equal to the sum of the squares of them. So, what straight line will have a square that is equal to the sum of AD squared and DB squared? Okay, so now we're saying by Euclid Book 1, proposition number 47, we say AD squared plus DB squared equals what? How are we going to find the what? Let them be placed so as to contain a right angle that is formed by AD and DB. Well, we did. That's a right angle. And let AB be joined. Well, as soon as you join these two together to form that right angle, you're going to draw this line right here. It is again manifest that the straight line, the square on which is equal to the sum of the squares on AD and DB is AB. So the missing sum here is AB squared, which is by Euclid Book 1, proposition number 47. Interesting formula. Now you have it. Alright. I will tell you more in a future video, so stay tuned.